All right, welcome. Today we're going to talk about a scientific tool that is, well, both a stroke of genius and a huge problem. We are diving into mercury porosimetry, a wild technique that's all about trying to measure, well, nothing. Empty space.
So let's just start with a question. Look at a block of concrete. It seems about as solid as it gets, right? But how in the world would you go about measuring all the tiny, invisible holes and tunnels inside of it? It's a really tricky problem, but it's one we absolutely have to solve to understand how strong and durable that concrete is going to be. Because when you zoom way in, you see this hidden world. That's not a solid rock. It's a microscopic maze. And this network of pores, it's not just dead space. Think of it as a superhighway for water and other chemicals to get inside and just wreak havoc over time. So yeah, being able to measure it, it's a pretty big deal.
And the challenge here is just immense. We're dealing with a massive range of sizes. These pores aren't all the same. You've got everything from millimeter-sized voids you could almost see with the naked eye, all the way down to nanometer-sized pores, which are on the scale of, like, individual molecules. So how can a single technique possibly measure a structure that's so incredibly complex?
Well, the solution that scientists came up with way back in the 1940s was, honestly, just brilliant. And it uses a liquid metal that, famously, does not like to get things wet: mercury. The technique is called Mercury Intrusion Porosimetry, or MIP, and the idea behind it is actually surprisingly simple.
So let me walk you through how this thing works. First, you take a dried piece of your sample and you stick it in a vacuum chamber to suck all the air out. Then you flood it with liquid mercury. Now, because mercury is non-wetting, it just sits there. It won't go into the pores on its own. But then you start applying pressure, a lot of pressure. This forces the mercury into the biggest, easiest pores first. As you keep cranking up that pressure, you force it into smaller and smaller and even smaller pores. By keeping track of how much mercury you've pushed in at each pressure step, you can basically create a map of the entire pore network.
And the whole thing is governed by a little piece of physics called the Washburn equation. Now, don't worry about the math here, but the takeaway is super simple. There's a direct link between the pressure you apply and the size of the pores the mercury can get into. A little bit of pressure fills the big pores. A ton of pressure fills the tiny little ones. It's just a really elegant way to turn pressure into a pore size map.
So it's a fantastic idea. Genius, right? But yeah, there's a pretty major catch. As this quote makes crystal clear, we are talking about mercury. And mercury is incredibly dangerous. This is where the story of our flawed genius starts to take a bit of a dork turn.
And the danger is really serious and kind of sneaky. Mercury vapors are totally invisible and have no smell, but they can do some devastating damage to your nervous system, your lungs, and your kidneys. And the really scary part is that the effects from long-term exposure, things like tremors or emotional problems, they might not even show up for months or sometimes even years.
So because of all that, you can't just run one of these experiments on a spare lab bench. No way. It needs its own dedicated, specially ventilated room. You have to wear full protective gear. There's even a rule against wearing jewelry because mercury will literally fuse with the gold in your ring. It is a high-stakes, high-maintenance operation. Okay, so it's dangerous, we get it. But, scientists work with dangerous stuff all the time if the data is worth it. The real problem, the plot twist, comes when you start to ask, what if, on top of all that risk, the data itself is just wrong? This is where a huge scientific debate really kicks off.
The whole controversy boils down to something called the ink bottle effect. Just picture it. You've got a big, wide-open cave that's connected to the outside world by one tiny, narrow tunnel. Well, the MIP technique can't actually see the big cave. All it sees is that tiny tunnel. So when the pressure gets high enough to finally shove mercury through that little tunnel, the machine logs the entire volume of that huge cave as belonging to a pore that's the size of that tiny little entrance.
And this just creates a massive disconnect between what the machine thinks is there and what's actually there. It's measuring the entry size, not the real pore size. This means it ends up wildly overestimating how many small pores there are because it's taking the volume of all those big ink bottles and assigning them to their tiny little necks. It's a really fundamental flaw in how the data gets interpreted. And here is the smoking gun. After you run the experiment and you release all that pressure, what happens to the mercury? Well, a whole lot of it, sometimes half of it, doesn't come back out. It gets stuck. It's permanently trapped inside those big ink bottle pores. It could get squeezed in through the narrow neck under pressure, but it can't get out. That trapped mercury is the physical proof that the ink bottle effect is real.
And the problems just keep piling up. The technique is based on a few other, let's just say, shaky assumptions. That core equation? It assumes all the pores are perfect little cylinders, which we know from the pictures just isn't true. It also can't measure any pores that aren't connected to the surface. And the final numbers you get are super sensitive to the parameters you plug in, like the exact contact angle of mercury, which is a whole other debate in itself. So let's just take a breath and recap. We have a technique that is highly toxic to use, and the results it gives you are based on a seriously flawed interpretation of what's going on. Which leads us to the biggest question of all. Why on earth is this still one of the most popular, widely used methods in the entire field? And the answer is actually really simple. Well, MIP is pretty terrible at giving you the absolute 100% true pore size distribution. It is exceptionally good and really reliable for comparison. Let's look at a perfect example. Here we're looking at 3 different concrete mixes with different amounts of water. Now, the exact numbers on the bottom axis, those specific pore sizes, they're probably wrong because of the ink bottle effect, but that doesn't matter. What matters is the trend. You can see it clear as day that as you use less water, the total porosity goes down, and that main peak shifts to the left, meaning the whole structure is getting finer. For telling you if Mix A is better than Mix B, MIP is absolutely fantastic. And here's another great use for it. We're looking at the same material, just as it gets older, from 1 day to 28 days. Again, just ignore the absolute numbers for a second. Look at the relative change. You can see the total porosity just plummeting, and the pore structure getting much, much finer as the cement hardens. MIP lets scientists literally watch this invisible process unfold and put a number on that change. So there you have it. That is the story of our flawed genius. The challenge was huge, measuring this invisible, complex network. The genius part was this beautifully simple idea of using pressurized mercury. The flaws, well, they're significant, it's dangerous, and what it measures is misleading. But its value is undeniable. As a tool to compare one material to another, or to see how a material changes over time, it's still one of the best things we've got. And all this really leaves us with a final, bigger question to chew on. The story of MIP is just a powerful reminder that every single tool we use has its own built-in biases and limitations. So when we're out there trying to measure the invisible parts of our world, how can we ever be sure that what we're seeing is the actual truth and not just a reflection of the tool we happen to be looking through?